Recording is rolling. It is Wednesday, March 11. You guys have this thermodynamics top page. So, guys, what we're going to do with this is I'm going to go over a bunch of these with you guys. We'll solve this in class. Guys, go ahead and just hold on to this. Don't even worry about turning it in. Just keep it for notes, though, because tomorrow I'm not going to be here. You guys can have a sub. I have Jerry Summons. But I'm going to give you, or have the sub give you guys a packet of thermodynamics puzzles. They'll all of them are pretty similar to these. So if you have these out with the notes that you guys are going to take today, then it'll probably help you guys solve those tomorrow. Okay? And you guys can work in teams tomorrow with those two, right? I want everybody to do the packet individually, but you guys can help each other out. Okay? And then and I left directions for the sub says due Monday, so he should give you a packet each individually, and then if you finish it in class, then awesome, you can, right? But otherwise, be due Monday, right? And so, any questions about what's going on? Okay, so. All right, so let's take a look here. Look here. Okay. Oh, I want to mention too. You guys remember these thumbnail notes you guys got very first day of school, like way back in August, right? So I was looking at these, and this looks pretty thorough. What you need now? Some of these we haven't hit yet. Like haven't pulled out the waterfall yet. Might pull that out later today. Okay? But some of these would be really helpful. Like, do you guys see this one that says change in entropy down here? Okay. So I did go through one of these with you guys. If you guys were keeping notes the other day, we did a calculation on this. But the thermo packet of puzzles tomorrow, there's a scenario that involves basically this, just the numbers might be a little bit different. Okay? But if you follow this, then you should be good. Okay. I wanted to point that one specifically because there's not one on this top page that's kind of like that. All right, so see what we got here. Number 28 at the top here. Also, we all have the same version, so we all have the same numbers today. How much heat is needed? So heat, that's a transfer of thermal energy. Right? How much heat is needed to change 50 grams of water at 25 degrees Celsius to just beginning to boil at 100 degrees Celsius? Okay? So, phase change here. Okay. Now, if you refer to your thumbnails, that reminds me a lot of, where'd it go? This one right here. Okay, you guys remember temperature versus heat energy for water? Okay. But here, bring up a large version. Here's a large version. Okay. And so we're going to use this as a roadmap. Now, we're talking about liquid water. Guys, isn't this right here liquid? So remember, we have solid here, liquid here, and here's like steam or gas right here. Okay? These flat bars are the phase transition. And we're going from 25 degrees Celsius to 100 degrees Celsius. You guys see we're going from this point to this point. You guys see that from here to here? Right? So, guys, what's the temperature change from 25 to 100 degrees Celsius? 75. Yeah, 75. Does everybody see 75 degrees Celsius change? Okay. And the question is, how much heat energy would that take? Which is say, like, how far to the right are we going from here to here? Okay. Because this would be in some about joules or kilojoules, something else. Okay. So the formula we're going to use is actually right here. It's just this blue formula. It says delta Q. Guys, what does delta Q mean again in thermodynamics? Change in thermal energy. Change in thermal energy. So heat, right? Okay, so we got this water on the stove. We're putting heat energy into it. How much? Oh, delta Q. Okay, that's what we're solving for. Here's M is the mass of water. Delta T is the change in temperature of water. Okay, what is C called again? What's that stand for? It's called specific heat capacity. Right. So water has a famous one. Here's liquid water, 4.18. Or here it is. Right. That could be joules per gram Kelvin, or so depending on what units you work on. Right, so here we got here. Right, so with all that in mind, any questions so far? Right, let's see. Let's do delta Q, which is what we're solving for. How much heat energy, thermal energy, heat, equals MC delta T. Okay. Now, as long as I have all my units straight, then I should get the correct number exactly. Okay. So maybe to be safe, I'll put everything in base SI units. Guys, I said 50 grams. Again, just to be safe, let's put that in kilograms. Why not? Okay. Guys, how many kilograms is 50 grams? Kilo is a factor of the what? 1,000, which is how many decimal places? Like three, right? Three. Okay. So you start with 50 and you roll back three places. Shouldn't it look like this? Okay, that would be kilograms. Okay. Yeah, so conversion there. Okay. Now, C, specific heat capacity of water. This is a number you'd have to have, right? Yeah, you guys have your thumbnail notes. So I put it here in joules per kilogram Kelvin. Actually, that's exactly what you need, isn't it? Joules per kilogram Kelvin. because all those are base SI units. So if you have your thumbnails tomorrow, then you have that number. So I'm gonna go 4,184. That's joules per kilogram Kelvin. You gotta be careful. Some textbooks put it in terms of like grams or something, so be careful there. Or kilojoules. Okay. And then what did you guys just tell me a few minutes ago was the change in temperature for this? 75 degrees Celsius. Because we're going to 100 degrees Celsius from 25 degrees Celsius. Guys, is a change in degrees Celsius, is that the same thing as a change in terms of Kelvin? Is a change in 1 degree Celsius equal to a change in 1 Kelvin? Is that the same thing?
No.
Yeah, it's the same thing.
What?
Or find a poster to back that up. Okay. Guys, let's go back and review some temperature scale. I got actually two that are kind of relevant to that. Let's go back and review that concept. Okay. So different temperature scales, ways to quantify what temperature is at. Like right now in this room, if you're thinking in American units, okay, it's probably at 70 something degrees Celsius. That's right here. Okay. If you translate over to Celsius, that's like 20 something degrees Celsius. Okay. That could be like Fahrenheit Celsius right here. Okay. But if you translate over to Kelvin, now let's compare Celsius and Kelvin, because that's probably what you're working with, like on a page, right? Okay. James, to go from 100, let's say 0 to 100, just because I see it right here, 0 to 100 degrees Celsius, freezing to boiling. Okay. Isn't that a change at 100 degrees Celsius? But what about on the Kelvin scale? Going from 273 to 373. Hey, is that the same change? That's also 100. Okay. Okay. Or if you like the equation form, whatever you have in Celsius, if you want the Kelvin value, like if you want the numerical value, you can add 273. But if you're talking about a change, right, this 273 difference would end up subtracting out. So a change in 1 degree Celsius and a change in 1 Kelvin is the same thing. So whenever you're working on temperature changes, it's actually okay to use either Kelvin or Celsius because it's the same either way, as long as it's a change. Okay. So let's put this all in and see if we can come up with an answer choice on the page. Got 0.05, 4184, 75. Okay. So I'm getting a number. It's 15,690. Okay. You guys, that number has a unit. What unit is on that number? What are we talking about? Delta Q is what again? Like thermal energy. Thermal, like change in. Well, delta is changing, right? So let's say change in or transfer of change in thermal energy. What's the unit for energy? The base SI unit. Joules. Yeah, joules. Right. And since all these values we did specifically put in base SI units, right? Like we converted now to kilograms and stuff. It's got to be joules. It's got to be joules. Okay. Now, as I'm looking at the answer choices, and you guys are too, it looks like all the answer choices are in kilojoules. So how do you go from joules to kilojoules? Yeah, divide by 1,000. So 15 point, I think 7. I rounded to on the paper kilojoules. Okay. You say it could be 15.7 kilojoules. Okay. And so, okay, so that's how much energy it took from the stove. Maybe there's like a flame burning on the stove, or maybe a stove range, however, right? That's how much electricity you have to buy from the electricity company if you have a stove range. Okay, you guys get that? All right, ready for your next one. Next one. All right, 32. We've got water flowing over a fall that's 125 meters high. Okay. I think I got a picture for that. Did I just point out this waterfall right here? This waterfall? I think we might be using that. The potential energy of the fall is converted all to thermal energy. Okay, so the water is going to fall and going to splash. I splash into some pool of water below. Okay. And when it splashes, where'd all the energy go? Well, it's not potential anymore. There's no height. It's not kinetic because it's not moving. Let's say it all goes to thermal. All goes to thermal. Is that going to heat up the water a little bit? Heat up the water? Right? Oh, again, I gave you guys the specific heat capacity of water, which you need to gain right here. Okay. So let's try this out. 32. Maybe I'll draw a picture, got a waterfall, got a pool, got a splash down here. And we got a height change of 125 meters. Okay. Okay. So we're going to use conservation of energy. You guys remember sum of energy initial equals sum of energy final? Way back last semester, we were using that to solve a bunch of puzzles. Okay. But we have a new energy form. Last semester, it was all mechanical energy. You've got some MGH, got the line up and be squared. You've got, now we have thermal energy. So what type of energy does the water start with at the top of the waterfall? Yeah, primarily potential. So I'm going to say mgh or mg delta h or some version of that. Okay. mgh. Right? And maybe it's moving a little slowly. It could maybe add a little kinetic, but I'm just gonna leave it there. And then when it goes to splash at the bottom, well, where did the energy go? Oh, okay, well, it probably went to raising the temperature a little bit. Like if you have a thermometer up here, you know, a thermometer down here, I bet it is relatively cold. This is relatively warm. Yeah, exaggerating a little bit. So, guys, what's the form for thermal energy? We just used it on the last question. It's what? Yeah, MC delta T. So the mass of water we're talking about times specific heat capacity times the change in temperature. And the question here is, what's the change in temperature? It says calculate change in temperature. Okay, so that's what we're headed for. Okay. Oh, wait. What is the mass of water? I never gave you the mass of water. Is that okay? Okay, so we have like a continuous stream of water. It's just flowing all day, every day. It's just going, it's going. Okay. Does it matter if it's been flowing for an hour or 24 hours or like 7 years? The temperature differential is going to be the same either way. Because eventually this water flows away and it's replaced with more splashing water. How does that show up in the map? Exactly. So quantity doesn't actually matter. Okay. And I think we have all these other numbers. So what do you guys want to use for, oh, actually, I put it in parentheses. I said use 10 meters per second squared. Okay. Even if you use 9.8, it'll be plenty close to whatever multiple choice. The height, oh, we got right here, 125. That's meters. And specific heat capacity of water, and it's 4184. That's joules per kilogram Kelvin. Okay. Right. There we go. Now we can solve for the change in temperature. Right. How much does the temperature rise? Okay. Does that make sense conceptually? Here, while you guys are digesting that, here, let's get a stay ahead of me. Let's get to the answer. Okay. Here's the posterized version that you have a little tiny thumbnail version of. Isn't that what we just did? We just did that. This is all in terms of variables. We got some numbers on this one. Okay, same thing. All right, you guys have that thumbnail. All right, so I'm just gonna say 10 times 125, then divide down 4184 by them. There. I'm getting a change in temperature of, I'm gonna round a little bit, 0.30. That would be degrees Celsius or 0.30 Kelvin. It's the same thing because it's a change, right? Okay, is that okay? And you guys get the same thing on your calculators? Okay, and oh yep, that's an answer choice. So that's gotta be it. All right. All right. All right, guys, get so far. All right. All right. Right. Let's do wait, 55. Next one here. I got a 50-gram piece of a mystery metal. Mystery metal at 100 degrees Celsius, placed in 200 grams of water at 20 degrees Celsius. That's about room temperature. Okay. The mixture reaches an equilibrium at 22 degrees Celsius. Okay. So it looks like the water warmed up a little bit and the metal cooled way down. Because the water only raised by about 2 degrees. And the metal cooled way down from 100 to 22. Because once they reach equilibrium, now they're all the same temperature. Now that process stops. Okay. What is the specific heat of the mystery metal? And if you know the specific heat, you could probably identify the metal itself, couldn't you? Right? Because we don't know what kind of metal is it copper, is it aluminum? What are we talking about here? Okay. But if you know this material property, you probably could. So we're going to do an equilibrium here. Now this one I also have a okay, yeah, and I'm seeing this showing up in your thumbnails too. Right. So let's do a force for the trees, a big picture of how it's going to work, and then we'll dive into the numbers. Okay. So the idea here is, here's my mystery metal. So drop this metal nugget into this big old glass of water. Okay. Now the metal starts out hot and the water is relatively cold. Okay. Do you guys think that some heat energy, some thermal energy, some heat is going to leave this metal and enter the water? Right. Okay, that's what this delta Q is. Right. That thermal energy leaving the metal and entering the water. Right. And that'll continue to happen until they reach thermal equilibrium. They have the same temperature. Right. Do you guys get that conceptually? Makes sense? Okay, so I'm going to say that the energy lost by the metal is exactly picked up by the water. That's an equation right there. It looks like first law of thermodynamics. Okay, first law. Okay. Okay. And how can you quantify thermal energy transfer. Oh, well, we did that for each of the last two questions. It was like MC delta T, wasn't it? MC delta T. So the MC delta T picked up by the water is exactly what was exported by the metal. Is that? Okay. All right, and then okay, no, this page I saw the rest in terms of variables and came up with temperature equilibrium. Okay, but we can pop in numbers probably about this stuff, and I think that'll be easier. So let's get that going. Gonna say 55, okay, and redraw that picture. We got a glass of water. We got some metal. It's emanating all this heat, all this thermal energy. I call it delta Q. Okay. Right. So I'm gonna say that here's my guiding principle here. The delta Q, let's say lost by the metal. Maybe I'll say negative because it's losing. Okay, equals the delta Q exactly picked up by the water. Okay, just like that. Okay. All right. So the mass of the metal times specific heat of metal times the change in temperature of the metal. Okay. And again, I'll throw in a negative because it's exporting the energy. Okay. And then the water, it got mass of water, specific heat of water, change in temperature of the water. Okay. So energy export, energy import, and it has to equate. Is there any questions so far? Okay. So far, no numbers even yet. Just keep it big picture, conceptual. Okay. But now it's number time. We can plug in some numbers here. So the mass of the metal, I told you 50 grams. Tell you what, I got grams of metal, and over here I also have grams of water. Is it okay if it's grams on the side and grams on the side because the grams cancel anyway? We could do all conversions, but that would cancel. So I'll just leave this 50. Okay, so 50, I'll call it grams. Okay. Okay, we're solving for the specific heat capacity of the metal. So there's our prize right there. That's on the prize. Okay. Change in temperature of the metal. Okay. It's what number would go right here, or maybe what little tiny little expression. How do you find change in temperature? What's the change in anything? Isn't its final value minus its initial value? Yeah. Right? Like change in velocity or change in momentum or change in whatever. It's final minus initial. Right? So I told you guys the final equilibrium temperature is 22 degrees Celsius.
20 minus 100.
Yeah, there you go. 22 minus 100. Okay. So the final is 22 degrees Celsius. The initial was 100 degrees Celsius. Right. Okay. And you might say, wait, shouldn't that be in Kelvin? But because it's a change, it's the same change either way, right? It's negative 78, either in Celsius or Kelvin. Change. Okay. How much water was there? Guys, here's another idea. Guys, if this metal was put in the Atlantic Ocean, is it going to change the temperature of the entire Atlantic Ocean? Not in any measurable way. Okay. But what if you had like a little tiny vial, like a little tiny cup? It could maybe raise the temperature of the water much more. Right. Right. So I think the more the mass of the water, the less the temperature change is going to be anyway for the water. I put 200 grams. So let's do 200 grams of water. Okay. Now again, you get it grams and grams. Don't have to worry about conversion just for that reason. Specific heat capacity of water. We're going 4184. This is a number we keep using over and over. That's joules per kilogram Kelvin. Okay. And the change in temperature of the water will go from what to what? It started at what and ended at what? Wait, you guys got the same numbers in front of you, right? The water started at what temperature and ended at what temperature? That's no. Yeah, it started at 20 degrees. So say something minus 20 degrees Celsius. And what did it end up at? Yeah, 22. Okay. Because they both had to end up at the same final temperature, didn't they? Okay. So the water started out at nice room temperature, 20 degrees Celsius. We put in this flaming hot piece of metal. Okay. And look what happened. The temperature of the metal crashed from 100 down to 22 degrees Celsius. And the temperature of the water rose a little bit, went from 20 to 22 degrees Celsius, right a little bit. Okay? And there's a couple of reasons why the temperature change for the metal is much more drastic than the water. One reason is that it's less massive. 50 grams compared to 200 grams. But even that's not a crazy ratio. Isn't that like a 1 to 4 ratio in terms of mass? Right? But there's a much more significant reason why the water would barely change its temperature. And what is that other reason? It's even more significant.
The thermal capacity.
Exactly. Yeah. It's the specific heat capacity for water is so huge compared to almost anything else. Right? Like if you throw out hydrogen here, ignore hydrogen, it would be the biggest number on this table. Okay? It's really, really, really hard to change the temperature of water. It takes a lot of energy to heat it up. And so, okay. So yeah, what you guys to see all those concepts, not just plugging and chugging with the math too. Because if you get the concepts, then math just falls out of it anyway. So we got -50, we got C metal, this is -78 equals, we got 200, 4184, and this would just be 2, right? Okay, so you guys know there are units attached to all these. Okay, so it looks like the specific heat capacity of the metal is going to be, these negatives cancel, right? Whatever this number comes out to, 200, 4184, 2 over, and then 50 and 78. Okay. And we'll have all base SI units. So this should be, no, that's not, hold on.
-78, right?
Yeah, it was negative, but this was also negative. And so the negatives canceled. Yeah. So negative. Okay. It did export import. Okay. Well, I'll tell you what, this will be some number of joules per kilogram Kelvin. Looks like I have joules per kilogram Kelvin on my paper, so I'm gonna have to do one more conversion after this. That's all right. Let's get this. Okay, so make sure you can correctly plug this in your calculator, because I have so many students who are not plugging this in correctly. And what they're mostly missing is that there are two numbers multiplied in the denominator. You have to group this together, right? Otherwise, guys, if you just hit divide and don't hit in parentheses down here, your calculator will divide by 50. Then it's going to turn around and multiply by 78. That's 78 in the numerator, and that will get you the wrong answer. So I would type like this: open parenthesis, got 200 by 4184 by 2. Close parenthesis, divide by, open parenthesis. You have to have an open parenthesis after you hit divide by, and then 50 by 78. Okay, so I'm looking at the number is 429, but that's joules per kilogram Kelvin. Okay. All the answer choices are in joules per gram Kelvin. So can you guys divide by 1,000? Okay. So that'd be 0.429. And that'd be joules per gram Kelvin. Okay. And that matches an answer choice. Okay, is that okay? Okay, so you guys are finishing writing that. Yeah, to go back to the big picture, right? The forest for the trees here. Okay. You got hot mixed metal and cold water. Drop the hot metal in cold water. The hot metal is going to cool down, and the temperature of water is going to go up. And that process continues to reach equilibrium. So the energy exported by the metal is imported by the water. Well, now we have a new formula for thermal energy, which is what this is. That's MC delta T, right, within any particular phase. There's no phase changes. The water's not boiling or anything. Okay, so the MC delta T lost by the metals picked up by the water. And you pretty much know all these values except for the specific heat capacity of the metal. So you do some algebra until the answer falls out. All right, guys, cover that? All right. All right, let's do a pretty similar one. Is the next one's pretty similar. Okay, so 56 here. Got 600 grams sample of water at 90 degrees Celsius. So really, that's scalding hot water. We pulled that off the stove. It's not quite boiling, but it's getting pretty close. They put 400 grams of water at room temperature, 20 degrees Celsius. What's the final temperature of the mixture? Okay, now it looks like these masses of water are not exactly 50-50, but fairly close. So I'm going to predict that the final temperature is going to be approximately halfway between, but maybe leaning a little bit more hot because they have more mass that's hot. Okay? And it is water versus water, so it's the same specific heat capacity. Okay. Now I think that process we're about to do is fairly similar to what we just did. Okay? Instead of metal and water, it's water and water. Okay. So let's do 56 here. Okay. So I have here. Let's draw a couple of glasses of water. Maybe we're mixing all this water together. Okay. So we have some hot water. We have some cold water. Okay. We're gonna mix this all together. Okay. So this over here started at 600 grams. and 90 degrees Celsius. This over here was 400 grams and 20 degrees Celsius. Okay. And they're gonna mix and make, well, what's the final temperature, right? You get that? Okay. Right, so let's see. Let's see. Right. I think we could do let's do the exact same setup we did for the last one. So I'll say mass of the hot specific heat capacity of water times the change in temperature of the hot mass. Okay. Now the hot mass is going to be losing energy, losing thermal energy because it's going to be cooling down. So I'll throw in negative for exporting the energy. So say negative delta Q for the hot equals delta Q for the cold water. Okay. Of course, it's going to make one giant mass of water too. So that's going to be that energy exported by the hot water is going to be exactly imported by the cold water. So mass of cold water, specific heat capacity of water in general, and then the change in temperature of the cold. Okay. All right, so I'm going to throw in one more line with variables before I throw some numbers in. Okay. So negative mass of hot, specific heat capacity of water. Okay. Now the change in temperature. You guys remember how change in temperature is the final value minus the initial value? Okay. Let's go T final minus T initial. Okay. Because what we don't know is the final temperature. Okay, and that's what we can solve for. Okay. Then over on this side, I'll have mass of the cold water, specific heat capacity of water in general. Okay. And then temperature final minus temperature initial cold. This is temperature initial hot. Maybe that. Okay. Okay. All right. Now I see how this is going to finish because we know all these. I gave all these numbers to you except the final temperature. We chose up in two places. That's okay. You use some algebra, tease that out, and solve for that. Is there any questions so far about why this is going to work? Okay. How the setup works? Okay. It's really the same setup as the question. Okay. The energy lost by the hot is picked up exactly by the cold. Right. First of all, thermo. All right. So let's throw some numbers in here. Here, leave some space here for my picture. My picture is right here. Okay. So mass of hot was 600 grams. So I'll put 600. Got grams right here. Okay. Specific. Guys, specific heat capacity of water. Since that shows up on both sides and everything's multiplied, could that cancel? Is that okay? Could that cancel? Right. Here's another reason to think why that's okay. Is what if I had a completely different experiment and it was olive oil? I had 400 grams of olive oil and 600 grams of olive oil, and they were the same initial temperature, and I mixed them together. Do you think that final outcome would be the same as it would be for the water? Yeah. One's going to cool down as much as what the other. It doesn't matter the material. So we just crossed out a material property because it's the same for both materials, and that's okay. Now, if you mix water and olive oil, you got to be careful. You can't pull it out. So I've got water and water. So we're going to simplify this a little bit. So that's nice. And so final temperature, we're solving for, we don't know. Okay. But I know the initial temperature of the hot, it was 90 degrees Celsius. So I'll go ahead and put in 90. Again, since we're talking about temperature changes, it looks like by the time I get T final, it will be in Celsius. So that's okay. When you're working on the temperature changes, it's okay to use either Celsius or Kelvin. That's okay, as long as it's a change. Okay. And mass cold over here at 400 grams of cold. We cancel out the specific heat capacity. And I'm looking for a temperature final again, shows up there. And the initial temperature was 20 degrees Celsius. Like that. Okay, now a little detail, make sure you have this. Remember how at the beginning I put a negative on this side? And I did this for the last one too, to show energy export. Okay. If you want to get all the algebra exactly right and get the exact correct answer, don't miss that little detail right there. Because otherwise we're like stumbling over negatives and wait, what are we subtracting what? Okay, so let's go ahead and expand this out, and the rest is just algebra. You guys see the rest is algebra? Okay. So everything up to this point is like conceptually how does energy flow, and here on out we're just doing some algebra. So I'm going to distribute here, get negative 600. I'll drop the units too, just to make it look a little easier. Negative 600 T. Okay, two negatives make a positive. 96 is 54. 0, 0, 0 equals 400 T, and then minus 8,0,0,0. I think it's like that, right? Are you guys getting the same thing? Is that working out? Same thing? Okay, so we're getting closer. I'll add over 600T. And I'll also add over 8,000. I think that's exactly what I want to do, right? Go like that. Okay. So it gives me 1,000 times the final temperature is, is this 62,000, I think? Right, units. Okay. I dropped all my units just to make the math look a little cleaner, but you guys know the units attached to these numbers. So we're real close. Guys, what's the last step? Divide by 1,000. So I'm getting final temperature is 62, and that would be, of course, degrees Celsius, because everything I put in Celsius, and that's fine because in the middle steps it was all temperature change, so it was perfectly fine. Okay. Yeah. Okay, so is that an answer choice? Yes, it is. Yes, it is an answer choice. So that's the equilibrium temperature. Okay. And then you go back to something I said right at the near the beginning. Remember, I was saying the masses of the water are kind of close to half and half. They're very similar to each other. So I thought the equilibrium should be, again, close to half, but weighted a little bit more towards the hot side. Well, the midway temperature would be 55 degrees because that's halfway between 20 and 90, isn't it? 55. Yeah, this is a little hotter than that. So yeah, that totally makes sense. Okay, guys, good. That's good. Okay. Now this next one right here is a whole adventure that I've done with you guys. So to save a little time, I'm just going to recap how to think about this. Okay. And what we're doing is, oh, whoops. Sorry. Never mind. I was looking at this diagram. Actually, you know what? Sorry about this. Okay, so this diagram here actually applies to the question on the backside at the top. I was just like spaced out weird. Okay. See, it says how much heat does it take to take 11 grams of ice at -10 degrees Celsius and turn it into steam at 120 degrees Celsius? Okay. So this one, I'm not going to do the numbers because those are also in your notes from the other day, but I will walk you guys through the process. Right, remind you guys like how to think about it. And I'll show you the numbers from the other day too, because I got those saved. Right. So the question is, like, using this as a roadmap, we're going from -10 degrees Celsius block of ice here to 100 something degrees steam, which is like over here. You see, it's going to be a 5-part process. First, we got to bring the ice up to begin to melt. That's this right here. It takes some energy. Okay? It's some form of delta Q equals MC delta T, but you have to play off the ice. Okay? Then we have to melt all the ice, and that's this leg of the journey right here. Hey guys, a phase change uses a different formula. That's M delta H. That's right here. That'll tell you how much energy it takes. You can't use anything with delta T because there is no delta T. Temperature is stuck. You see that? Okay. Now, once you've melted the entire ice cube, now you go back to delta Q's MC delta T. But now you have the C for liquid water. And that'll take you all the way up to 100 degrees Celsius. Now the water starts to boil. Right? And okay, now we're undergoing another phase change. So now we're back to delta Q equals M delta H. Now it's delta H for vaporization. Boil all the way. Now, once you've boiled away all the water, now you have a bunch of steam. It's the same mass. The mass is still the same, right? Now you can keep heating that steam until you reach your final temperature, okay? Now, I'll show you guys the notes that are in a video from the other day. Okay, so I use it, different mass and blah, 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 right? But it's a very similar process. So I want to remind you guys, I started from -5 degrees, and this adventure I cut off right at the point that I boiled away all the steam, and I didn't heat the steam anymore, but you guys could do that too, right? So I had a 4-part journey, okay? Right, so first I did MC delta T to bring the ice to begin to melt. That took that much energy. Then I had to melt all the ice. And the formula changed to M delta H of fusion. Here's the delta H of fusion. If I want you to apply these numbers, I would give these numbers to you. I would not expect you to memorize the numbers. But the process you can know. Okay, so now we melted away all the ice. That's part 2. Part 3 is I got to bring the water to begin to boil. So now we're back to MC delta T. The delta T. Guys, what's the delta T? What's the change in temperature going from just barely melted to beginning to boil? If it just barely melted, right? Just melted, what's the temperature? Is it 0 degrees Celsius? If it begins to boil, what temperature does it take to begin to boil water? 100 degrees Celsius, basically, right? But let's assume we're at sea level for all these, right? So what's the change from 0 to 100? It would be 100, right? Can you guys remember that for tomorrow when you have to apply that tomorrow? Because you're going to see the same question basically, right? Just different numbers. Okay, so now it takes that much energy to bring the water to begin to boil. Okay. And last step is we had to boil all the water away. So now we're back to M delta H, but this delta H of vaporization. So after boiling all the water away. Okay. Okay, so. All right, so you guys have that in your notes. So just to give you guys the essential notes, I'll move on here. Okay. Let's I want to do one more with you guys. Let's do one more. Okay. We're gonna do number 65 right here. 65. Okay. And then I got some video demos that I wanted to fit into. So see 65 right here. It says a 10-gram lead bullet. Now lead, that's a material, so I tell you the specific capacity right here. Now this isn't joules per gram Kelvin. Yeah, let's just stick to grams for this because I got grams here and grams here, so that'll be better. Okay. Maybe or no, do I want to do that? Because maybe I'll change my mind, but let's see. Right? Moving at 250 meters per second strikes a tree and is brought to a stop. Okay. Guys, if you fire a bullet into a block of wood or a tree and you feel that wood right after the bullet collided with it, is that wood going to be very, very cold or hot? You just fired a bullet into wood.
Oh, yeah.
It's going to be very hot, isn't it? Right. The idea here is that all that kinetic energy that was in the motion of the bullet, that's what kinetic energy is, energy in motion, went into thermal energy. And let's assume that it, oh, okay, right. Guys, we're doing a big assumption here. Suppose it all stays in the bullet somehow, right? Which is a ridiculous assumption, but let's just make believe just for the math. Okay? How much would the temperature of the bullet rise? Or maybe a better way to phrase that more realistically is what's the maximum possible temperature rise of the bullet? Okay. So I'm going to say the change in mechanical energy of the bullet, which is really the change in kinetic energy, all goes into thermal energy. Right. So we're going from kinetic to thermal. Would it be like that? Kinetic to thermal? Right? Now, change in kinetic, if it goes from some kinetic to 0, I could just call it. What formula can I put right here? What formula? 1/2, what? Yeah, 1/2 mv squared. You guys remember that from last semester? Mechanical energy? Right? Earlier today, we did one with a waterfall, and we were using MGH potential energy. Actually, I think this is fairly similar thought process to that, isn't it? Right? We're just going kinetic to thermal. Right? And then for delta Q, now here's a formula we've used a few times today already. It's what? M C delta T. MC delta T. Right? And the question we're targeting here is what's the maximum possible temperature rise of the bullet? Right? That makes sense. Right? This form of energy turns into this form of energy. Okay. Oh, you know what? Guess what cancels out?
Nice.
Yeah, the mass of the bullet. That doesn't even matter anyway. It doesn't matter if you have a small bullet or a big bullet. It doesn't matter how fast it goes, though. That matters. So let's run this here. 1/2. What did I tell you how fast it was going? 250 meters per second. Okay. Now 250 meters per second. Okay. And then don't forget to square that. Don't square that. Okay. I think I changed my mind on the units. Let's go ahead and just stick to base SI units. Just be really, really careful that we're not off by a factor of 1,000 or something silly. Okay. So I gave you the specific heat capacity of lead and joules per gram Kelvin. Let's change that to joules per kilogram Kelvin. Guys, kilo could be 1,000 times, right? So let's call that actually 159. And that's joules per kilogram Kelvin. Okay, so we're all in base SI units that can't make any silly mistakes about decimal places. Okay. Okay. And then there's going to be some resulting change in temperature. Okay. Sure. Okay. So I think all I got to do is divide down this 159. Let's go 1/2 times 250 squared over 159. I'm looking at a change in temperature of 196.54. It could be degrees Celsius or Kelvin because it's a change, so it's okay either way. Okay. Is that an answer choice? Yes, it is. 197. 197. Okay, you guys see that? Is that? Okay. All right. Any questions about any of these? Okay. So what I hope you guys did today is first got good notes. Guys, hold on to this paper. Don't worry about turning in. I will give you guys points in the grade book. And this will be the last grade of this quarter. Oh yeah, right.
What's the answer to 57 and 64? I was not.
But we didn't do that. We didn't do Yeah, we didn't do this.
Okay,
Right.
okay.
Right. But this, at least the other thing I want you guys to get out is to really see the big picture of like how energy is transferring, and really conservation of energy from last semester. That's really very similar thought process to what we've been doing all day today. Okay? Except now we have a new energy form, which is this thermal energy, okay? Which might look like this sometimes. Okay? Right? Okay. Okay. So I think if you guys kept good notes, you'll be ready for that puzzle packet tomorrow. And of course, you guys can help each other out. I left directions for the sub that says that too. You guys can help each other out. But we're going to end class here with a video demo.